presentation is the Africa Nano3 leveraging NANOscience, nanotechnology and nanosatellites for Africa-centered connectivity solutions by Mr. Ifriky Tadadjeu Sokeng from Cape Peninsula University of Technology. Please.
Good morning, everybody. Good morning, everybody. Awesome. Glad that's better. I'm Ifriky Tadadjeu Sokeng, and today I'm talking to you about a mission idea that was developed within the framework of a partnership between my university and the space program in it, the University of South Africa, and Itemba Labs National Research Foundation's research facility that has a branch in Cape Town and in Gauteng in South Africa. It generally starts off with a problem that needs a solution for which space offers the best solution. And we're trying to solve the problem of the random guy somewhere in sub-Saharan Africa who needs help and can't cry out for help. We want to make sure that there's a possibility to get to him. And we reckon that if there were such a system, crises like the ongoing Ebola would have been handled better. In fact, we could have had data that would allow for the virus, is it the virus? I think it's the virus. The virus mapping that would have cleared a lot of paranoia that we have now. What we propose as a solution is a dedicated communication and connectivity mission that we want to do with micro/nanosatellites. Why micro/nanosatellites? Because we know how to do it. That's no other answer. And it's the most affordable way to do it. There's a further problem. There isn't much money, and therefore one needs to be efficient. So we want to increase functionality per unit mass. The way it's done these days is using nanosatellites, nanoscience and nanotechnology, which makes sense so far. We reckon it's not a bad idea, but can it be done in Africa? Yes, it can. In fact, there's a lot of good work going on in South Africa and in other parts of Africa in nanoscience and nanotechnology. This work is very space applicable. It can increase functionality per unit mass, but it simply isn't used for space applications yet. So we want to tap into that. Now, so we came with a collaborative concept where CPUT FSATI designs the communication and connectivity mission with a constellation of nanosatellites. That's not an exaggerated figure. We reckon it should be applicable for 50 years because in the context in Africa, we need to overcome a lot of barriers and we need to demonstrate there's a lot of usefulness before people actually start buying into it. So it is realistic to say 50 years for it to be effective. In fact, in 50 years, I reckon that there will be only 5 to 10 years of effective work done. The rest will be to show that it makes sense to go ahead and do it. Now, we call for people in the African nanoscience community to tell us about the work that they do that is space applicable. Good news, we got people to answer that call, Itemba Labs and UNISA. Why? Because when it comes to nanoscience and nanotechnology, they know how to do it. And we need them to get more efficient space missions. Now, in terms of mission objectives, therefore, if I look at the connectivity, we need this guy to be able indeed to send a message. We need this message to be transferred effectively. We need that the link be scalable to cater for bigger volumes. And we also want to use the fact that cell phones are all over Africa and use a cell phone as primary messaging interface. In terms of technology demonstration, what Itemba Labs and UNISA propose is vanadium dioxide that they want to demonstrate in space as a passive means to do thermal regulation. In fact, if you coat anything with VO2, it would maintain the temperature on the other side always below 70 degrees Celsius, which is very useful in space and can add functionality to nanosatellites. There's also the DRA antenna arrays that we want to demonstrate in space. Now, in terms of mission concepts, believe it or not, there are cell phones in places in Africa so remote that there isn't GSM network coverage. I don't know why there are cell phones that far, but there are cell phones just about everywhere in Africa. So we want to tap into that and provide a third-party communications device that would allow this cell phone to communicate with the device through a dedicated SIM card. This device in turn communicates with a satellite, that sends his SOS message to the nearest emergency care center. Now, this emergency care center has affiliates, professionals of a medical field or law enforcement field. So they receive it as an SMS that they can therefore respond, and it would get back to the guy who needs it somewhere. The good news is his message goes around with his GPS position. Therefore, as soon as they get it, they know where he is and they can get to him. The users here, there would be the guy, the random guy in the random place, and the emergency care practitioners. And the users on the other side, for us who designed the mission, would be the scientists who provide the science payloads. And well, that includes Itemba Labs in this particular case, and CPU TF-SATI. If I tell you a bit more about VO2, the reason why it's so sexy, allow me to say it, is that if you look at the transmission with wavelength, notice that at around past 70 degrees, it stops transmitting in the infrared, which accounts for why the temperature always stays below the transition temperature. If you look at the transmittance versus temperature, these are different wavelengths, and you see what happens when you get to the infrared range. It just cuts off. Because it is reversible, you have a hysteresis loop as the film cools down again. This is important because you can see the resistance dropping with temperature. This helps us to monitor the health of the film in space by simply measuring the resistance across a piece of VO2. Key performance parameters include, well, it is a mainly comms mission. That's what accounts for the longevity of it. Pretty self-explanatory, but I need to mention that when it comes to ADCS, we would turn to Stellenbosch because they know how to do it and they can achieve that accuracy. But I have to mention that I did not put in the paper that the dielectric antenna array can achieve tracking in a solid angle of 120 degrees, because when I wrote the paper, I did not know that yet. The guy who's designing it told it to me last week, which means that even if we have orbit degradation, we can still find the satellite we need to communicate with and talk to it, which is pretty good news, I must say. The satellites are mainly 2U satellites. One is the ADCS-U, the other is a communications unit. And if there is experiments, we add a third unit to the constellation. Now, this is the vanadium dioxide experiment. In this case, this is the dielectric antenna array experiment. And the subsystems are pretty standard. We're not reinventing any wheel, really. We're just testing new technology on experiments, which makes it quite easy to implement. In terms of data link, this is the slide just to show you the interface for the cell phones, which is a SIM card, and the maximum node capacity that we're looking at for this particular communication mission. Link budget, we're using UHF and S-band to make life easy, just use two communication bands. I think this table is also pretty self-explanatory. We can get back to it if during the question and answer session, need be. We achieve less than 3 minutes maximum revisit time at 800 kilometers. This is a diagram generated by STK, and you can have a look at the orbit parameters over there. Also pretty self-explanatory. You can get back to it during the questions if need be. Standard implementation plan, except for the deorbiting, where we want to detach the ADCS unit. That will allow for a tether in between, and we can use the tethering solution to deorbiting the satellite. Pretty fancy, because at 800 kilometers, it's not very practical to count on drag and deploy a sail. In terms of business feasibility, this, I have to say, this is not a spin-off company model. This is just to ensure that within Africa, we can have a self-sustained and a self-sufficient mission in terms of finances. You can have a look at what we bargain on. the universities get very involved. This table tells you 5 years of financial plan, and we're not thumb-sucking them. If you consider that you pay much less because you're an academic institution, it makes sense to go with these figures and come with that kind of a table. We can come back to these numbers during the Q&A. The future, well, we extend applicability and add some support along the equatorial plane and grow, and when we're done growing, we grow some more. Ladies and gentlemen, that's the end of my story. Thanks for your attention.
Thank you very much. So, could you give me the questions?
I just have a question about, can you not do all this much cheaper with the cell phone network, the GSM network? Why do you need the satellites? Because if it's a remote area and the guys can phone into the ground station of your satellite, you need a ground station somewhere, so you might as well have a GSM node in place of the ground station to have connectivity in those remote areas without current cell phone network.
Yeah, we did think about it, and there isn't coverage everywhere, unfortunately. There are places where it would be quite difficult to achieve coverage, but there is life there. We're not saying the coverage won't get there in time. That's why we want a mission that has extended applicability, because it's a good idea to work hand in hand with the people who provide the coverage, so that we can achieve much more with this kind of a mission in terms of African development as a whole. But for the meantime, if there were a lot, if GSM alone could do the job, if I take Ebola again, life would have been much easier in terms of how we deal with it. So we reckon it is not, it will take time, but we're not saying the networks won't have that kind of coverage. It's not there yet, and we want to tap into that. No, not grounds. We have a third-party portable device. It's useful also for guys who go on safari far away, where they don't want to be anywhere. They need to be able to call for help as well. And it won't be as cheap as having a Turaya phone, or, no offense to Iridium, but an Iridium phone too.
But if you solve this SOS problem this way, you need a certain density of nodes on the ground. Can you a little bit elaborate how you determine this density and how you place your ground stations or your nodes or ground nodes?
Well, the third party, the way it works, you have the emergency care centers. Could be a hospital, could be a fire brigade, could be a police station. They, like I said, the business model, pay a fee for the service to the university next to them that provides the third-party handheld devices that the users, the general people in the population, can now get. Depending on the density, we can have a solution where we have one major station that can allow for communication, or physical handheld devices. We propose a deployable dipole solution that can achieve UHF. In that sense, people have the third-party devices with them as an extra device. The universities can take care of the maintenance. That increases the skill level and human capacity building in the field. I don't know if it answers the question.
Yeah, it's answering the question basically on the ground. And there's another density to be discussed. That's the number of satellites and the number of orbits.
That is to achieve the coverage, the required coverage. It will take time to populate the different orbital planes to the desired point. But unfortunately, that cannot be scaled in time because we're counting on agreements and piggybacking and so on and so forth. Luckily, last week we had the solution about orbit degradation where one can track a satellite and talk to it.
Yeah, but you must have at least a theoretical solution. How many?
We haven't gone that.
Okay.
We haven't gone that far.
I'm interested in multiple access to the satellite. So the many people try to send the data to the satellite all at once. And so how you can discriminate each messages? And for example, maybe the 1,000 users will send data to the satellite almost all at the same time. And so how the satellite can discriminate such kind of the much number of these datas?
For this mission, at the start point, in terms of emergency, we don't anticipate 1,000 at the same time. But I do agree, we have considered, because it's scalable, when we escalate to messaging, and so we have to come with more sophisticated solutions. One of the reasons why we use IPv6 is anticipating a shift in technology where IPv4 is forgotten. It is catered for, and it will allow us to upgrade without having to do too much work if we already cater for it now. In terms of handling the error, we will need to be creative about it. In terms of emergency, we don't anticipate that big, these big volumes. But yes, we have to take it into consideration to scale the mission. We have to consider it. We haven't gone that far to handle these big volumes yet.
Quick question about your link budget. I was wondering what you expect the antenna gain to be on the spacecraft. That was the antenna gain on the spacecraft itself. You had a horn. Oh, hold on, there's more. And you have 800 kilometers as the distance, but that assumes the satellite is purely overhead. Are you assuming mostly you'll have short passes with the satellite nearby, or you go?
No, we anticipate about 15.28 minutes of a pass time. The reason for the orbit is we want to reduce the probability that someone sends a message and it doesn't get through. So we want to be able to resend the messages and have it through to only to the same satellite. Also, to reduce the probability that a message is going to the guy and it doesn't get through. In terms of
so there the only issue is that with a foldable dipole on the ground with very little gain.
Oh,
you're probably going to need some gain on the top.
That's why we're using a horn antenna to talk to the ground as for the ground stations, and the deployable the dipoles on the antenna on the satellites as well for the UHF.
Yeah, it's just that gain is not in there.
Oh no, sorry about
I'm
that.
wondering. The other question is, and again, just you're going to 800 kilometers. Debris-wise is not the best place to be. I know you have a deorbit device, but that increases complexity on the system. So there's a trade there between if you just went down to like 650, you wouldn't have to worry about it anymore. So
yeah, it does increase complexity. We trust the ESL guys. Thank you.
Okay, thank you very much.